Let's talk about speculative decoding. One of those techniques that sounds almost too clever to be real, but it's now running inside production inference stacks at Google, Meta, and every serious LLM deployment team. If you're interviewing for a senior AI engineering role and someone asks how you'd cut LLM latency without sacrificing output quality, speculative decoding is the answer that separates the engineers who've actually shipped inference systems from the ones who just read the papers. So what is it? At its core, speculative decoding is a way to generate multiple tokens in a single forward pass of your large model. And the reason that matters is rooted in a fundamental truth about transformer inference. It's memory bandwidth bound, not compute bound. Your expensive target model, the 70 billion parameter beast, spends most of its time waiting for weights to load from GPU memory, not actually doing matrix multiplications. So if you can verify several tokens in one pass instead of generating one token per pass, you've just multiplied your effective throughput without changing the model at all. Here's how it actually works. You have two models, the draft model and the target model. The draft model is small and fast. Think a 7 billion parameter version or even a 1 billion parameter distilled sibling of your main model. The target model is your production LLM, the one whose quality you actually care about. In each step of generation, instead of asking the target model for one token, you let the draft model speculatively generate a sequence, say 4 or 5 tokens ahead. Then you run the target model once, feeding it the entire speculated sequence in a single forward pass, and you check whether the target model would have agreed with each of those tokens. The verification step is elegant. Because of how autoregressive transformers work, a single forward pass over a sequence of k tokens gives you the probability distribution for all k positions simultaneously. So you can check whether the draft model's prediction at each position matches what the target model would have chosen, using an acceptance criterion. If the token passes the acceptance threshold, you keep it. If it fails at position 3, you discard tokens 3, 4, and 5, replace token 3 with the target model's actual choice, and start a new round of speculation from there. What you've achieved is this. On a good run where the draft model mostly agrees with the target model, you've generated 4 or 5 tokens at the cost of roughly one target model forward pass. Your wall clock latency per output token drops dramatically. Real-world numbers range from 1.5 to 3 times speedup, depending on the task, and how well the draft model tracks the target. Now let's talk about the production trade-offs, because this is where interviews get interesting and where most teams make mistakes when they first deploy this. The first trade-off is draft model alignment. The whole thing collapses if your draft model disagrees with the target model too often. Acceptance rate, the fraction of speculated tokens that pass verification, is your core operational metric. If your acceptance rate drops below 50%, you're actually slower than vanilla autoregressive decoding because you're doing extra compute for the draft model plus the full verification pass, and throwing away most of the speculated tokens anyway. The sweet spot for real production wins is an acceptance rate of 70% or above. You achieve that by ensuring the draft model was trained on the same distribution, ideally distilled from the target model itself. The second trade-off is memory pressure. You now have two models loaded simultaneously. On a system already pushing GPU memory limits, that's a real constraint. Teams handle this in a few ways. Some use quantized draft models, running the draft in int8 or even int4 to keep its memory footprint tiny. Others use draft models that share the same architecture backbone as the target, with the same tokenizer and embedding table, so you can share those weights. A third approach, called Medusa heads, skips the separate draft model entirely and instead adds extra prediction heads on top of the target model itself. Those heads speculate future tokens in parallel with the current token generation at the cost of a small increase in per-pass compute. The third trade-off is the impact on sampling strategies. Speculative decoding is mathematically lossless when you're doing greedy decoding or when you use the careful rejection sampling scheme that Leviathan et al. Described in the original paper. The output distribution is provably identical to what you'd get from the target model alone. But when you start layering on top P sampling, repetition penalties, and custom logic processors, the acceptance criterion gets more complex. Teams often have to write custom verification logic for their specific sampling configurations, which adds operational complexity. There's also latency variance to think about. In vanilla autoregressive decoding, every token takes roughly the same amount of time, which makes your P99 latency predictable. With speculative decoding, you have high variance. Sometimes you accept 4 tokens in a single pass. Sometimes you accept 1. For streaming use cases where you're pushing tokens to a user interface, that variance can create perceptible stuttering if your serving layer isn't designed to handle it. You want to emit tokens as they're accepted within a speculation round, which requires your streaming logic to be aware of the batching behavior of speculative rounds. Finally, batch size interacts awkwardly with speculative decoding. The speedup is most pronounced at batch size 1, a single request getting low latency responses. As you increase batch size, the memory bandwidth bottleneck that makes speculative decoding valuable becomes less severe because you're amortizing weight loads across many requests. This means speculative decoding is a tool for latency-sensitive single request or small batch scenarios, not for maximizing throughput in a high concurrency system. In practice, production systems often use speculative decoding for interactive chat endpoints while using continuous batching without speculation for bulk generation or async workloads. Let me give you a few interview-ready phrases that demonstrate deep understanding of this topic. First, we use instrument acceptance rate as a real-time metric alongside TTFD and token throughput, and we gate speculative decoding behind a dynamic routing layer that disables it for request patterns, like long structured outputs, where we've measured acceptance rates below our threshold. Second, for the draft model selection, I'd evaluate Medusa heads first because they eliminate the memory pressure of a second model, then fall back to a distilled standalone draft if Medusa training hurts target model quality on our task distribution. Third, the losslessness guarantee in the original paper assumes exact greedy sampling at the verification step. Once we add temperature and top P, we need to adapt the acceptance criterion using the corrected distribution. That's the version in the Chun et al. And Leviathan et al. Papers. So the output distribution remains provably equivalent to the target model alone. And fourth, in our serving architecture, I treat speculative decoding as a request-level decision made by the router, not a system-wide toggle. High-priority interactive requests get speculation for latency. High batch size throughput jobs don't, because the gain disappears and the overhead adds up. The reason speculative decoding is such a rich interview topic is that it sits at the intersection of model architecture, serving infrastructure, sampling theory, and operational metrics. Understanding it end-to-end signals that you've thought deeply about how transformers actually execute in production, not just how they're trained. And in a world where inference costs are often 10 times training costs at scale, that knowledge is directly tied to business impact. If you want to go deeper, the key papers are Leviathan et al. From Google in 2023, Chun et al. From DeepMind in the same year, and the Medusa paper from Together AI. Between those three, you'll have everything you need to design, implement, and defend a speculative decoding system in any interview or architecture review.